Okay, so now we're going to look at On Your Own 6-4. In On Your Own 6-4, we have our equation there, and we are given that we have 3.49 moles of HCl, and that's added to excess calcium carbonate and excess water. How many moles of calcium chloride will be made? So of the calcium chloride component, which is that one, okay? So we're going from moles to moles, which comes from the equation. Someone had a question in class, why does it even say excess CaCO3 and excess water? All that means when they're telling me that is that this is this is excess and this is excess. It makes this the limiting reactant. And that means we can always find how much we're going to produce by the limiting reactant. Okay, essentially the problem is done the same, but we do want to understand what it means to have the limiting reactant. It will determine how much product we make, okay? So I'm looking to compare my HCl with the CaCl2H12O6. So I start with the 3.49 HCl, moles of HCl. Start with what I know. I need a mole ratio, which comes from the book. And so in the book, I see that there are 2 moles of the hydrochloric acid for every 1 mole of the calcium chloride hydrate. So what I'm looking for is the calcium chloride hydrate. I'm putting that on top. And over here, then I had 2 moles of HCl. So the moles of HCl cancel. 3.49 times 1 divided by 2. So basically you're just dividing by 2. And so the answer ends up being 1.74 something. It actually rounds to 1.75 if we want 3 sig figs. So we'll have 1.75 moles of the CaCl2H12O6. And I'm still looking offside my paper. Sorry, I'm trying to pay attention to that. There we go. Okay. That is the end of the On Your Own problems. So, the next thing we're talking about is Gay-Lussac's law. And Gay-Lussac's law is going to tell us something particular of another way to relate things. So let's look first and see if there were any more notes we needed to fill in. I think we filled in all of that. Okay, so we're on the top of page 51 in our notes. And it says, explain what the French chemist Joseph-Louis Gay-Lussac determined about stoichiometric coefficients. And here's what he realized. He realized this right here, that the stoichiometric coefficients can be used on gases. And so that's kind of what he's saying. The stoichiometric coefficients relate the volume of gases, okay, as well as number of moles. So it works either way. So Gay-Lussac's law can be used, but only on gases. So in example 6.5, we had this equation over here where we start with C8H18. We add O2 and get carbon dioxide and water. So this is combustion. They tell us we're combusting here. So we build our basic equation. We go back then and balance our equation, and we're at this point. So we're going to use this as our finished equation when we look in our example. So basically, when I look at these stoichiometric coefficients, I have 12 liters of the octane. So I have 12 liters, so this is example 6.5, of the C8H18, and I am wanting to find out how many liters of carbon dioxide would be formed. And so I kind of told the kids there's two ways you can do that. You can use that if there is a, let's see, if 16 moles of CO2 go with 2 moles of the C8H18, then you can also say 16 liters of CO2 goes with 2 liters of C8H18. So that's all they're saying is you can not only write a conversion factor about the moles from the equation, but you can write one about the liters. And so we can use the conversion factor of liters if we'd like to. And so we could say 12 liters of C8H18 times 16 liters of CO2 over 2 liters of C8H18. And then in the end, we mark out our liters. We'll have 12 times 8, basically. And that's 96 liters of CO2. And this only works when you have gases. So you have to look at your equation and you have to see those little phases of G down there. And that's one of the reasons why we go ahead and include phases sometimes in the equations. So you can use it if there's a G. You may not use it on anything else, okay? Just when you're comparing gases, you can say, hey, that tells me something about volumes. So take a second to work the on your own problem, 6.5. Just maybe pause the video and then work on your own 6.5, and then you can unpause it and make sure you worked it right. Okay? So the chemist starts with 3.67 liters of CO2 gas, and he wants to find out how many liters of HCl that would be. Well, here's what I know. If I go and look at my equation, the mole ratio of HCl and CO2 is going to be the same. So 2 moles of HCl is 1 CO2. That's what I know. So that also tells me, because of Gay-Lussac's law, I can say that 2 liters of HCl is 1 liter of CO2. So I just know this is my conversion factor. So I take the 3.7 liters of CO2 times, I'm gonna put 1 liter of CO2 on bottom, 2 liters of HCl on top, and I'll just take 3.67 and multiply that by 2. Okay, so the answer on that on your own 6.5 would be 7.34 liters of HCl. Okay, so that's 6.5 for you. So here's a couple things we know. We know that Gay-Lussac's law is worked only on gases. It does not let us convert moles to liters, okay, or anything like that. It just lets us say, if I know the volume of one gas, I can find the volume of another gas in the problem, okay, by looking at the mole ratio. That's all it does, okay? So let's go on to mass relationships.